Hello, welcome to my channel. In the class 12 today we will learn a new topic, electromagnetic induction. Before starting this topic, I would like to say some importance and history about why should learn this topic. In the long time ago, electricity and magnetism, these two phenomena were not related. They were supposed to be unrelated and separate. But in the 19th century, the successful experiments were performed on electric current by Oersted and Ampere, and they established the interrelation between electricity and magnetism. They found that moving charges produce magnetic field, and if a magnetic compass is placed in the vicinity of a current carrying conductor, it deflects. These facts naturally raises the question, like, is the converse effect is possible? Do the moving magnets produce electric current? Does nature permits the relation between electricity and magnetism? The answer for these answer is definitely yes. Faraday and Henry both demonstrated that electric current were induced whenever magnetic field linked with the closed coil changes. Thus, the phenomenon of electromagnetic induction is not only of the theoretical or academic interest, but also of practical utility. Imagine a world without electricity, without trains, without telephones, without personal computers. How will you feel? So, Henry and Faraday, they have led directly to the development of modern day generators and transformers. Today's civilization owes its progress to a great extent to the discovery of electromagnetic induction. Let us see what is electromagnetic induction. The experimental work by Faraday, I have shown here a conducting loop connected with a sensitive galvanometer. This is galvanometer and a bar magnet. It is placed with north pole here, so magnetic field lines are passing through the conducting loop. If we take away this bar magnet, suppose up to this point, what will happen? That magnetic field lines passing through the conducting loop will decrease. That is, magnetic field link with the closed circuit changes, and we find that galvanometer shows the deflection. Similarly, if north pole is brought closer to the loop, again the deflection is shown by galvanometer but in opposite direction. Same deflection, set of deflections is observed when instead of north pole, a south pole of bar magnet is taken away or brought closer to the conducting loop, but deflections are opposite those who are observed in case of north pole. One more thing, that if you keep the magnet at the same place and bring the closed loop closer to the magnet or take it away, the deflections are observed in the galvanometer, that is, induced current is produced. Also, if the relative motion between them, either you bring magnet closer to the loop or you bring loop closer to the magnet at a faster rate, we find that larger is the amount of deflection. In the second experiment, what was observed, that instead of magnet, this is a same galvanometer attached with the conducting loop, and instead of magnet there is another coil and it is attached with the battery like this. So current flows in this way. So instead of magnet taking away or bringing closer to the loop, we replace the magnet by this current carrying coil, and we observe the same result, that whenever the coil is brought closer to the loop, deflection is observed in this galvanometer, indicating that there is induced current produced in the conductor. And when this coil number 2, suppose I say it is C2 and it is C1, when C2 is taken away, the deflection is observed in the galvanometer, but in the opposite direction. So in these two experiments, we have seen that if there is a relative motion between bar magnet and the current and conducting loop, and this current carrying coil and conducting loop, we found that induced current is produced in the conducting loop. What about the third experiment, that if there is a conducting loop or a coil attached with the sensitive galvanometer and another coil is placed near it and having a battery connected with it and a tapping key. Suppose this is key K. Whenever the key is pressed, a momentary deflection is shown by galvanometer, indicating that a magnetic induced current or induced EMF is produced in this coil. If tapping key is remained pressed for a long time, no change, no deflection is shown by the galvanometer. And when this tapping key is switched off, it is released. As soon as this key is released, again the deflection is, momentary deflection is found in this galvanometer, but in opposite direction. What these experiments show, that whenever there is a magnetic field linked with a closed circuit, changes, induced EMF is produced in this circuit. And Faraday formulated the law based on electromagnetic induction. Before telling these laws, we will discuss these laws. First, we will find that what is magnetic flux. You know, electric flux, we have seen that what is electric flux? Electric flux is electric field and area vector dot product. So magnetic flux is magnetic field and area, its dot product. It is a scalar quantity and its unit is Tesla meter square. It can be written as BA cos theta. Magnetic flux depends on magnetic field, area vector and angle between magnetic field and area vector of the loop. What is area vector? A perpendicular drawn on the loop. How will you define magnetic flux? The total number of magnetic field lines passing normally through the loop. Magnetic field depends on, this magnetic flux depends on area, magnetic flux depends on magnetic field and magnetic flux depends on orientation of vector, that is cos theta. How? Look, that if there is a uniform magnetic field and if we take a loop of lesser area, suppose this one, and if we take a loop of larger area, what we observe, that more will be the field lines passing through this loop, so more will be the flux linked with that loop. So larger is the area, larger is the flux. Similarly, if the magnetic field increases, then flux will also increase. And cos theta, how can you say that if there is a loop and it is placed here in the magnetic field and this is the normal on the loop. Suppose this is the normal on the loop. Magnetic field lines are, suppose, in this way. Can you tell me what is the magnetic flux? In this situation, what will be the magnetic flux? What is theta? 90. Cos 90, 0. What will be the magnetic flux? 0. What I mean to say that in the definition we have seen the magnetic field lines passing normally through the loop. Here, if the suppose this is the circle and the loop is placed like this, that this is the magnetic field direction like this. So magnetic field lines are passing here like this from left to right. No magnetic field line is passing through the loop. And you know what is the area? This is the area vector. What is the angle? 90. So magnetic flux is 0. Cos 90 is 0. If the magnetic field is shown like this, that this is the loop and this is the magnetic field, and suppose this is the area vector. This is the angle between magnetic field and area vector. How will you find that phi is directly proportional to cos theta? So whatever is the magnetic field line, they are passing perpendicular through the loop. So in this way you will find that in this direction the magnetic field will be B cos theta. So if the magnetic field lines, they are passing through this way, that is all the field lines they are passing through the loop, then magnetic flux will be maximum. So we have seen what is magnetic flux and how it changes. In this way, the Faraday's first law of electromagnetic induction, it is given by Faraday. And how can you learn, how will you say what is Faraday's first law? So Faraday's first law of electromagnetic induction. This law says that if there is a change in magnetic flux linked with a closed loop and EMF is induced in that loop, this EMF lasts till the change of magnetic flux remains present. How will you say this? What this law confirms, that there is a continuous change in magnetic field linked with a closed circuit, only then there will be the continuous production of EMF or the induced current in that circuit. And this is the principle of generator. This phenomenon is called electromagnetic induction. So whatever is Faraday's first law, this is the definition of electromagnetic induction. This is the principle of generator, that the continuous flux change linked with the closed circuit produces magnetic EMF, induced EMF, and this EMF lasts in the circuit till the change of flux takes place. What is the second law of Faraday? Second law of Faraday is the mathematical form of it. It says that magnitude of EMF, this is induced EMF produced in a closed circuit, is directly proportional to the time rate of change of magnetic flux linked with it. Again I am saying, this second law of Faraday says that magnitude of induced EMF produced in a circuit is directly proportional to the time rate of change of flux linked with it. We can write this EMF equal to this minus d phi by dt. This minus sign has its own importance and it is used to express the direction of induced current by the Lenz rule. Lenz rule tells the direction of induced current, we will discuss later on. So what is Faraday's first law? what is electromagnetic induction, what is induced EMF and its relation we have seen today, and how many ways are there to produce induced EMF. You know, induced EMF is produced when the flux linked with the circuit in which the EMF is induced, with that circuit the flux linked is changing. There are how many ways, so many ways to change the flux linked with the circuit. How can you change the flux? By changing, look, the first way, if you take the magnetic field as B equal to 5T or B equal to 7 by T, you know how the magnetic field is changing with time, and in this changing magnetic field you place a closed circuit. You will find there will be the continuous rate of change of flux you will find, and there will be the continuous production of EMF. Similarly, how can you find the flux change? We can find the flux change by having the loop rotated in a magnetic field. Now this time magnetic field is uniform, but if you rotate the loop about certain axis, look here that in the magnetic field, if this is the loop and this is the area vector, is it visible? And if you rotate the loop, this is the axis, about the axis, if you rotate the loop, then theta will change, magnetic field is constant, so you will find that there will be the induced EMF because d phi by dt. In the same way, if there is a magnetic field and what you do, take a closed circuit, closed coil, and from this outside the magnetic field you bring it closer to the within the magnetic field. What will you find? There was no field lines. Now magnetic field lines will increase as the loop will enter, and you will find from 0 to certain magnetic number of field lines will pass through the loop, and there will be the induced EMF produced in that loop or induced current. Main thing is that the magnetic flux linked with the closed circuit should change, and this magnetic flux changing magnetic flux will produce the induced EMF or induced current in the circuit. Today we have discussed what is electromagnetic induction. In the next lecture we will discuss about the direction of induced current, and there are so many ways how the induced EMF is produced in a closed circuit. Thank you.